Hello, my name is Tomáš Masařík and I will present you an algorithm that solves maximum weighted independent set in quasi-polynomial time on a graph with no long clause. So this is joint work with Peter Gartland and Daniel Lochtanov from University of California, Santa Barbara, and Marcin Pilipčuk, Michal Pilipčuk, and Pavel Řanževský, and me, all of us from University of Warsaw. So let me introduce the problem, although I think that most of you have heard about it. So it's notoriously hard, the famous graph problem. We are given graph with possible weights on vertices, and we are asking for a subset of vertices such that the induced graph doesn't have on those vertices doesn't have any edges, and we would like to maximize the weight of such induced subgraph. So here on this example, you can see an instance and a solution in the degenerate case that where all the weights are of size 1. So, because this, as I mentioned, this problem is notoriously hard and notoriously hard to approximate. So we would like to know how it behaves on hereditary graph class. So those are graph class that are closed under vertex deletion operation. And in other words, those are graph class that are characterized by a collection of forbidden induced subgraphs. The word induced here is important, and in fact, in the whole talk, whenever I say induced, whenever I say some subgraph, I always mean induced. So, but this collection may be infinite, but we are asking what happens if we forbid just one single forbidden induced subgraph. So not the whole class of it, the whole collection of it, but just single one of them. So this question was partially answered in 80s by Alexev, and he shown a couple of hardnesses. So in case of H not being a forest, there is a hardness if a graph has 2 degree 3 vertices. Again, we have NP hardness. And in the last case, if there is a connected component with more than 3 leaves, then we also have hardness. So what remains for this forbidden graph H is path on T vertices or subdivided claw. So those are, say, two options that are potential candidates for polynomial time algorithms. So let's look at the history. So a positive result is given in 2008 by Lozin and Milanic, and they showed that this fork graph if we forbid it, we can solve maximum weighted independent set in polynomial time. And this was also extended to P5, so we forbid path on P5 vertices, but it was already quite complicated, and this paper of Lochtanov, Vachel, and Wilanger introduced a very interesting concept that people were building upon later. So it's already somewhat complicated, and the current knowledge of polynomial time algorithms stops with P6, with the work of Grzesik, Klimoshova, Pilipčuk, and Pilipčuk. They managed to show polynomial algorithm there, but it's already very involved. So that's as far as we know about polynomial running time, and it's not really much, right? So what about some weaker result than polynomial? So there was QP-TAS and sub-exponential algorithm on STT3 graphs in 2020, and recently afterwards there was breakthrough into quasi-polynomial barrier of Gartland and Lochtanov on PT3 graphs, and this was subsequently simplified by Pilipčuk and Řanževský, and also the whole framework was generalized to C of length at least T3, so this is not forbidding single graph, but forbidding all cycles of length at least T. So this is an exception of forbidding just one graph in this talk. And as well, if we return to STT3 graphs, but we say that the input graph has bounded degree, then this can be also solved in polynomial time. And in this talk, we actually managed to push this quasi-polynomial running time to the most complicated possible graph class, which is we are forbidding STT. In fact, we can forbid a finite number of copies of STT. So this is really pushing it to the boundary. So this is the largest possible case which can admit such a running time. Okay, so for the rest of my talk, I will try to give you glimpse of ideas and glimpse of proofs of how we solve this problem. So let me jump into our toolbox. So first tool in our toolbox is extended history decomposition. So don't be intimidated by the definition. I will try to point to the most crucial parts of this definition, but it will get a bit technical. So, but try to follow the ideas. Okay, so we get a graph, and we would like to present its extended history decomposition, which is a pair of two things. One is graph h. So here is on this example, h is some other graph, probably much smaller than g, and some function eta that tells us what parts of G are mapped into elements of H. So, for example, those elements of H can be either vertices of H, edges of H, or even triangles of H. And this eta, there are some important things about eta. So eta is partition of vertices of G. So each vertex of G has to belong into some element of eta. Okay, then for every set of edges that are incident to one vertex, like this one on the picture, I require all those edges to be there. So in fact, this is a bit more complicated. So for each edge of H, if I look at vertices of G that are mapped to HH, then actually I will also specify to which vertex they will belong to. They can belong to both two vertices, but for those that belongs to the same vertex, and for the other one that belongs to the same vertex, so if I take two neighboring edges, two adjacent edges, and the parts that belong to this vertex, then actually all those edges between the vertices of G has to be there. So this is strict condition. And the third condition is also about edges of G, and it says that edges of G can be only in some specific places. So edges of G can be either can be in those cases where they actually have to be, right, in those two adjacent edges close to one vertex, and the other options are that they are inside some elements of eta. So for example, they are inside one edge, or they are inside vertex of H, or they are inside the triangle. That's possible that the two vertices there can have H. And also what's possible, it's possible to go from this vertex set of H to some adjacent edge close to this vertex. So those dashed lines actually suggest possible edges. So those are not mandatory edges, but possible edges. And the same for triangles. If you are in intersection of those edges that belongs to both vertices, then this allows us to have an edge to triangle. Okay, so we will get the intuition on the next slide. So let's move to the next slide that shows us some use. Because for now you may be wondering, maybe we can just map the whole G into some edge of into some vertex of H, into just one vertex, and then we satisfy all the requirements. We mapped all the vertices of G somewhere, we preserved all the edges are inside one element of H, and we are happy. But actually, this extended strip decomposition is useful if we put some more restriction on it. So it was developed by Chunovsky and Seymour for 3-net theorem, and this is actually our second tool. So let me present the theorem. So we have graph G and we have set Z, subset of vertices, and our question now is to find in polynomial time two outputs, either induced subtree on at least 3 elements of Z. So I will get some induced subtree on 3 vertices out of all vertices I put into Z. That's understandable. But what happens if there is no such outcome? Okay, in that case, Chudnovsky and Seymour returns a certificate that no such triple of vertices of Z admits induced subtree on them. And this certificate is actually extended state decomposition with some additional property of placing those vertices in Z into leaves of H. And they will be actually the only elements in those leaves of H. And nothing will be in the vertex backs of those leaves, so those will be empty, in fact. Okay, so why this is a certificate? And now you will also understand the intuition. So think of connecting two of those vertices in Z, and think of how such a path can look like. So for example, this red path connecting Z2 and Z3, okay, it can be there. It's induced. That's great. So, but now if we would like to connect there Z4, for example, like this, then actually, because of the structure of extended state decomposition, because of all those edges being mandatory from those interfaces that belongs to one vertex, then this will certify this edge that indeed this 3 on Z2, Z3, Z4 is not induced, because there is this triangle. Okay, so we can look at one more path. So maybe we would like to connect this Z1 with some other vertices with this path Z2 and Z3. So if we try to connect it somewhere else, okay, here is again this edge that's mandatory. So again, there we have triangle. So you now see the pattern. Whenever we connect, we are connecting from 3 sides, then there actually has to be this triangle in between. So now we see the power of extended state decomposition. If we have this additional requirement, then those vertices that we are interested in, this set Z, will be spread into leaves of H. Okay, so to recall, this theorem actually tells us that either there is this induced subtree, or we get this certificate which is extended state decomposition. Okay, so let's learn another tool, and this tool is called Jarfash path analog for STT-free graphs. So if you are not familiar with Jarfash path, let me mention the argument first. So we start with some vertex and we remove neighborhood of it, and then the rest of the graph will split into connected components. Maybe just one component, but at most one of such components will have size and half, or weight and half. So we pick one vertex out of it, and again we look at how it splits into some connected components. Maybe at most one of them can be of size and half, and so then we pick another vertex, we remove neighborhood, and eventually we will end. And now we can easily observe that this path that we were building is actually an induced path. So in this, if we are in PT-free graphs, which are not, but if we are in PT-free graphs, then this path has at most -1 vertices. This is nice. In our case of STT-free graphs, this path can be the whole graph can be path, so this path can be very long. But what this analog of Jarfash path tool told us is that there is a set P of logarithmic size such that if we remove its neighborhood, we get refined extended state decomposition. So what we mean refined, there every particle, which is, you can think of this edge or vertex or a triangle back or some slightly bigger components than this, has weight half of weight of G. So in a sense, before, for PT-free graphs, it was actually very easy. All those parts were connected components of size and half, and it was very easy to do divide and conquer algorithms there. Now we get refined external decomposition. So this is also a very good tool to actually get divide and conquer, because we can have this drop in size of half, and there are some algorithms that allows us to combine it. Okay, this is nice, but we actually get this set P of potential logarithmic size and its neighborhood, and we have to deal with it somehow. So that's what we built in this paper, and we showed lemma that actually we can in polynomial time take extended state decomposition which was refined, so all those particles were small, and we can add one more vertex to that. So this was extended state decomposition of G minus V, and we can add V, and sorry, we are trying to add V, and our lemma says that we get three possible outcomes. Either we find an STTT, or we find another good outcome for our algorithm that we will discuss at the end, which is dominated balance separator, dominated by some small number of vertices and balanced, which is also a very good outcome. Or we are able actually to add V while still keeping the property of refined extended state decomposition. So in the algorithmic part, we already seen work with K-dominated V-balance separators. So just to recall the definition, this is a set S which is dominated by K vertices, and it's of size B, or of weight at most B. And this was shown in the original PT3 algorithm for this original quasi-polynomial algorithms on PT3 graphs by Gartland and Lochstanov. But actually, we cannot use this anymore. Like, first of all, STT3 graphs doesn't have to have K-dominating B-balance separators because of, for example, line graph of a click. So those even doesn't have to exist. But there is another difficulty. So let's see. So let's first look into packing lemma here. So it says that we have a STT3 graph, and we have some subset of vertices. So those are supposed separators, and we assume that no vertex belongs to more than C of such sets. Then, if we get sufficiently big the size of this family, so there is this size of C, but also some T constant and S from the separator, then we say that no component of G has more than 3/4 of vertices of M. So then we say that actually G had small components, and it's good for quasi-polynomial branching. So why I am saying it first without telling you what are S-boosted balance separators? Because similar statement was true and was shown for PT3 graphs, where we just could replace boosted balance separator, our new term, with K-dominated B-balance separators, and that was how the original proof was done by Gartland and Lochstanov. But actually, this is not true anymore for those K-dominated B-balance separators, because, for example, if you take path, and if you would like to split graph into components of size and half, say, then picking those colors will do that. Those are balance separators, and they are of size 2, so even more so dominated. But if you think of long paths can be of length n, then we can have like order of n such balance separators. So there is actually, instead of product of constant, we can have many of such separators. If we just aim for like 2 dominated half balance separators, then this is not achievable. And that is why in this paper we developed boosted balance separators, which has some stronger requirements. So let's see. So this is only simplified definition, but let's just to capture the idea is that so this is again neighborhood of some set dominated by that set of at most s vertices, and we would like the components of g minus g without the separator to be of size smaller that of size number of vertices over 16s squared, where this square factor growth is actually important because it prevents us constructing such examples with path. So we really would like to break it into significantly smaller components than before. Okay, so with this definition, actually this packing lemma works. So if we go through it once more, we are given a family of those S-boosted balance separators, and we assume that no vertex belongs to more than C of them. Then actually, if this family is big, then G has to have small components. Okay, and having small components is again a good thing to quasi-polynomial branching. So that's what we used. And the last ingredient in branching is actually how to get those boosted balance separators, because as you remember, our main structural lemma says that we get actually k-dominated B balance separator. So there is another branching that actually provided k-dominated B balance separators is going to give us either the same outcome, so G already having small components, or eventually it will give us this CT boosted balance separator. So this is another quasi-polynomial branching that that we have, and actually our algorithm is a composition of all those quasi-polynomial branchings. But that's nice about quasi-polynomial time, that we can compose it nicely, and that's very high level idea of how our algorithm works. So here I would like to say one more thing. So here we recurse only on relevant vertices. So those are vertices in components which are still large, so not yet captured by this boosted balance separator. So we had to use weights there, and actually we had to work with weighted problems. So not only that we solve weighted version of independent set, but actually it was crucial to push our branching through. Okay, so let me conclude with open question. Of course, we would like to know if it's possible to design polynomial algorithm for STT3 graphs or not. It don't have to be possible, but it would be nice to know. Probably it would be good to have some structure that use STT3ness everywhere, if it exists, because so far we were using extrinsic decomposition which enforce to us some property only for some special set of vertices, and then we were composing those decompositions. So in some sense we used it on multiple places, and also it was used in this Jarfash path analog tool that we used, but still we don't enforce any property of being STT3 everywhere. There can be parts that doesn't require it. So that would be good, and ideally if such structure admits some polynomial time algorithm solving maximum weighted independent set of those small parts, then this might be way to obtain polynomial algorithm. But of course we don't know anything yet about PT3 graphs, and for them we even didn't need to use any complicated structure in the first place. Basically, their Jarfash path and components of size and half are as far as we need with the structure, and so so even those PT3 graphs would be very interesting to know if we can do polynomial time or not. So with that, I will finish my talk. Thank you very much for your attention.